Welcome to Life with David. I'm David, and today I'm going to add the Terminal Interface Monitor, or TIM, to my 6502 emulator that runs on a Raspberry Pi Pico. This will give us the ability to program the 6502 the same way I did in the beginning of the microcomputer era. I'll also use the TIM to load EHBasic into the emulator and to act as the I/O interface with EHBasic. So why don't you join me as we do some real work using my bare metal RP2040 6502 emulator. I've documented the MOS Technologies 6530-004 TIM chip in several videos. This companion chip to the 6502 allowed developers to program and debug 6502 code using a simple ASCII terminal. This was key to moving away from the blinking lights display in order to speed up program development. One of my goals during the development of the RP2040 6502 emulator was to implement the TIM chip program. Since I finished testing the emulator, my next step is to implement the TIM. However, to do that, I have to set up reliable communications between an external terminal and the 6502 program by using the emulator as a data conduit. In fact, the TIM will play an important role in those communications. Let's review the TIM chip to see how this works. The 6530-004 includes 16 I/O pins, 1 kilobyte of ROM from 700 hex to 73FF hex, which contains the TIM program, and 64 bytes of RAM. Serial communication is accomplished by using bit banging and 2 I/O pins, one for input and one for output. For the emulator, I'll replace the bit banging I/O with serial communications from the RP2040 UART0. The trick is how to get the data from the outside terminal into the 6502 emulator. When data is received by UART0, it throws an interrupt which calls this interrupt service routine. Data is read from the UART0 data register. Then the upper 24 bits are discarded and the 8-bit character is placed in the 6502 UART received data register, which is at E800 hex. Then bit 0 on the 6502 UART status register, which is located at E805 hex, is set, indicating a character is available. The TIM spins on E805, waiting for bit 0 to set, at which time it will grab the character from E800 and continue on. When data is written from the TIM, it's placed in the 6502 UART transmit register, which is located at E801 hex, and bit 5 of the 6502 UART status register is cleared. I'll only check the status right after the 6502 writes anything to memory. In the 1-byte write routine in the emulator, after the data has been written to memory, I'll check if the write address was to the 6502 UART status register or E805. If not, I'll just continue on. However, if it was, then I'll check if bit 5 was cleared. If it was cleared, then the program will grab the character from E801 and send it to UART0 for transmission. Then bit 5 of the 6502 UART status register will be set, indicating that it's ready to accept more data. Don't get hung up on the addresses of the 6502 UART registers. Those are arbitrary locations that I chose. They could have been anywhere. I figured that E800 was pretty much out of the way. That's why I put them there. I rewrote the TIM program slightly to ditch the bit banging and add UART functionality. I also added a non-halting read, which will check if a character is available on the fly. Then I relocated the program from its original starting location of 7000 hex to D000 hex. This time we'll use CA65 and LD65, written by Ulrich von Basowitz, to compile and link the TIM 6502 program. I'll go through the details now. Inside the TIM program, I'll specify the 6502 memory origin of the program, D000 hex. I'll also declare that the TIM resides in a segment named code. We'll use that later during the link process to locate it in the proper spot in the 6502 memory. As a reminder, even though the 6502 memory actually resides from 2002.0000 hex to 2003.0000 hex inside the RP2040 memory map, I'll refer to it using a 4-digit hexadecimal address, just like a 6502 would. The original TIM character input and output routines reside at 72E9 and 72C6 hex respectively. I'll include the original TIM manual, including the program listing with the rest of the project files. I'll put a link in the description below. Since the RP2040 UART0 is now doing all the dirty work of timing the serial connection, the routines can be much simpler. I'll overwrite them with the new routines and have enough space left over to add a non-halting character input and customized character output routine for additional programs like EHBasic. I'll share those new I/O routine locations shortly. Note that I've included the 6502 reset and interrupt vectors in the segment vectors starting at FFF8 hex. These are needed for proper operation of the TIM program, including the break instruction. Let's peek under the hood of the make CA65 command. This will give you some of the tools to customize it if you want. First, this command will compile the file picotim.asm using no specific 6502 system. It will generate a list file as well as the object file. Other options are available. Simply type CA65-H to see them. Next, we need to link the program. I want to transfer over the entire 64K 6502 memory image at once, so I have to slot the programs properly into 6502 memory space here. I've created a configuration file, ptim_ld65.cfg, to detail the memory map. This will slot the segment's code and vectors into memory starting at D000 and FFF8 respectively. This command executes LD65 to link the object file using the desired configuration file and will generate the EMU program.prg file, which is the desired 6502 memory image. In the emulator program, I'll change the program entry to the cold entry point of the relocated TIM program, D006 hex. Then I'll combine the 6502 program with the RP2040 6502 emulator program by using make full to create a .uf2 image to download to the Pico. I discussed that process in the last video. I'll leave a link in the description below. Let's try it out. I use HyperTerminal since I can easily transmit text files between the TIM and the terminal. I'm using the same TTL to USB converter that I used in Chapter 3. Please see that video for more information. Like I did with PuTTY in that video, I set the COM port to 8, 115,200 baud, 8 data bits, 1 stop bit, and no parity. For text transfers, I also added a 1 millisecond delay to each character and a 5 millisecond delay at the end of each line. This gives TIM enough time to process the data and move it to memory. Next, copy over the UF2 file into the Pico. I'll include the UF2 file with the rest of the project files if you don't want to go through the entire compile and link process. If everything worked properly, you should see the opening prompt for TIM. Here you can view and change the program counter, accumulator, X and Y registers, the processor status, and the stack register. Simply type a colon to make the changes. You can also start a program by modifying the program counter, typing enter, and then G for go. Memory can be viewed using the M command and can be changed using a colon. As a reminder, you can only use capital letters with TIM. I go into much more detail in my TIM video. I'll leave the link in the description below. The relocated TIM contains character input and output routines that will be used by other 6502 programs. The new input routine is located at D2E9, and the new output routine is located at D2C6 hex. I've also added a non-halting input routine located at D2F4 as needed by some other programs. Let's try entering and running a program using the TIM. I'll enter the character printing test program included in the TIM manual, with the modified character I/O routine locations and run it. After entering the program, I'll change the program counter to the beginning of the program and then type G to go. As expected, all characters are output to the terminal. Now that TIM is working, let's try EHBasic. This program came out in 1976 and was packaged and distributed by Itty Bitty Computers. I'll include the original manual complete with my notes from the day with the rest of the project files. I've included a MOS Technologies hexadecimal text file with the proper input and output vectors for this emulator. In Hyperterminal, type LH, then select Transfer and Send Text File. Point to the Pico-Tim EHBasic file and click on Open. The file should start transferring over. It's pretty slow, but after a minute, the program should be loaded in. Remember, now you're getting a taste of what early computing was like. The file transfer process is ended with a semicolon and a return. I've added that to the EHBasic hex file, but you might have to do it manually for other files. Type R to bring up the processor status register, and then type :0200 and enter. Then type G to start EHBasic. I'll type a simple program. If you make a mistake, you can backspace and overwrite the character. At the time, I thought this was awesome, since before EHBasic, I didn't have any editing capability. Remember, this is 1970s microcomputing. After we list the program, I'll run it, and it works just as expected. We can save the program by using Transfer, Receive Text File, and then listing the program. After the program is done listing, stop the text receive. Before you can use the file, you must edit it to remove extraneous commands and characters. To use the file, clear the old program, then use Transfer, Send Text File to send the file to EHBasic. Back in the mid-70s, we didn't have a host computer. We had to output the program using paper tape or a tape recorder. We also had to walk uphill both ways to school. There are many games written for EHBasic back in the day. Here I am playing tic-tac-toe. As you can see, I've never been a gamer. I even suck at tic-tac-toe. EHBasic was groundbreaking at the time. But now that we have more memory, we want things like floating point math, variable names longer than one character, and for next loops. Time to port EHBasic to the emulator. EnhancedBasic was written by Lee Davidson from the UK. Sadly, he passed away in 2013. However, his program lives on. EHBasic is quite powerful and simple to port on any 6502 system. It only requires 13 kilobytes of RAM, a non-halting character input routine, and a character output routine. Since I have 64K of RAM, and I've already written that non-halting input routine, I'm ready to go. Inside the Pico-Tim EHBasic.asm file, near the end and just below label PG2_tabs, I'll add the character input and output routine vectors. The non-halting keyboard input routine starts at D2F4 hex, and the EHBasic output routine starts at D2CE hex. I won't add dedicated load and save routines since I can use text send and receive to load and save the programs. EHBasic is much larger than EHBasic, so I want to load this program into the Pico at the same time I load the emulator and the TIM programs. That means I'll have to combine the TIM and EHBasic programs into the 6502 image. I set the EHBasic origin to 8000 hex and assign it a new segment, code 2. In the TIM program, I'll add include Pico-Tim EHBasic.asm to add the EHBasic program into the 6502 compilation and linking process. I'll create a new LD65 configuration, ptim EHBasic LD65.cfg, adding segment code 2, which starts at address 8000 hex. I'll also update the makefile to include the new LD65 configuration file, and then I'm ready to compile and link the programs using the normal process. Using the command prompt from inside the project file, type make clean, then type make CA65. Finally, type make full. We can see from the final .dis file that the EHBasic program is located at 2002.8000 hex, which is 800 hex in the 6502 world. Likewise, the TIM program and the vectors are also located in the correct location. Start Hyperterminal and download the UF2 file to the Pico. TIM will start. Change the program counter to 8000 hex, the cold start for EHBasic. Then type return and G for go. EHBasic will respond with a memory size prompt. Type return and EHBasic will launch. Here's a quick little program to demonstrate how we can save and load a file. Here I save the program using capture text. After the program has been listed, I'll stop text capture and I'll edit the file to remove extra commands and text that I don't need. Back in EHBasic, I'll type new, which will delete the program in memory. Then I'll send the text file, which will load in the program. How fast is the Pico TIM compared to a hardware 1 MHz 6502 TIM in a real-world application? I used identical EHBasic counting programs. After 50 iterations by the Pico TIM, the 1 MHz 6502 had only completed 8 iterations, approximately 6¼ times slower. That means the Pico TIM has an equivalent clock frequency of 6.25 MHz. Note that this emulator is not cycle accurate, meaning some of the emulated cycles take more clock cycles and some take less than a standard 6502. I imagine that making it cycle accurate will slow the emulator down. However, I'm really satisfied with the results. Thanks for joining me today. This time I added some programs to do real work inside the 6502 Pico emulator. That included the original terminal interface monitor, TinyBasic, and EHBasic. I also demonstrated how to use the CA65 compiler to add other programs you might want to use. Completing this project has been a big milestone. I've been thinking about it in one form or another for a couple years. Last time I said I'd like to utilize the onboard USB connection to eliminate the serial to USB adapter that I'm currently using. However, my initial research has led me to believe that mere mortals should not delve into the bare metal inner workings of USB. I'm trying to resist getting sucked into that rabbit hole. Let me know if you have any ideas. In the meantime, I've got a couple other projects to get caught up on, so stay tuned. If you like this video, or you think someone else might, please give it a thumbs up. If not, give it a thumbs down. The more likes this video has, the more YouTube will recommend it to others. Also, please leave a comment or suggestion for things to do. I hope to do more of these videos, so please subscribe and click on the bell for notifications of new videos. Let's get together next time for another day in Life with David. See you soon!